Hi class, this is a video on the Doppler effect, or sometimes called the Doppler shift. This occurs for any type of wave if the source of that wave is moving towards or away from the observer of that wave. So this could be for a sound wave, or it could be for any type of electromagnetic wave or any other type of wave for that matter. You've probably actually experienced this for sound waves. For example, if this was an ambulance or a fire truck with a siren, so it's producing sound waves, and it's producing sound waves of some wavelength or some pitch or some tone. If that source of sound waves is moving towards you, it's going to sound higher pitched. And you may have experienced this, that when an ambulance is traveling towards you, or a fire truck, the siren sounds higher pitch. Well, that's higher pitch means shorter wavelength. And so what's happening is that the ambulance or the fire truck is emitting the sound at its normal wavelength. However, because it's moving towards you, those sound waves get compressed, they get shortened, and what actually reaches your ear is a wave of a shorter wavelength or higher pitch. And then similarly, if it's moving away from you, it's still emitting the sound at whatever its wavelength is, but if it's moving away from you, those sound waves get stretched out, and so you would hear it as a lower pitch or longer wavelength sound. This also occurs for visible light, which is a form of an electromagnetic wave. So, for example, if this source was emitting green light, and if that source was moving sufficiently fast towards this observer could measure this as being blue light if that green wavelength got compressed so much that now it appears as blue. Well, it turns out this would have to be moving at a very, very high speed for that to happen. But if that was occurring, then this observer over here would be observing that source of green light. However, that green wavelength would get stretched out and it would look red. So we call this blue shifting, and we call this red shifting. So if the light is compressed because the source is moving towards the observer, we say that it's blue shifted. And if the light is stretched out to longer wavelengths because it's moving away from the observer, we say it's red shifted. And so in astronomy, we are the observer. So this is like the person with the telescope looking at some source of light and looking at the light after it's been either stretched or compressed like that. That's the general description of the Doppler shift. Here's the equation right here. So we want to learn how to use this equation. And we'll just define all these symbols. We have lambda here, and we have lambda naught. That's how you read this. The lambda with the 0 subscript, that's read lambda naught. So this is lambda minus lambda naught. Lambda is the wavelength of the light that's actually recorded or observed by the observer. So that would be the blue wavelength for this woman. It would be the red wavelength for this man. Lambda naught is the wavelength at which the light is emitted from the source. So that would be the wavelength, in the example that I've been describing, that would be the wavelength of the green light that the source emitted it at. And so if you somehow know what that wavelength that the light was emitted at, so you would know lambda naught, and then you record or you observe what lambda is, the wavelength that you receive it at, then you can take the difference between those two wavelengths and you can divide it by the wavelength that you know it's emitted at. And when you do that, when you do all this math, this turns out to equal the velocity or speed of the light source divided by the speed of light. Now, when you look at this equation here, the velocity, v, it can turn out to be positive or negative. And the way that it becomes positive or negative is based on whether this term right here, lambda minus lambda naught, this is the thing that can be positive or negative. If lambda right here, this wavelength of the blue light, if this is smaller than lambda naught would be the green light. So that is the case for the woman here. If lambda is smaller than lambda naught, this term becomes negative. This is a positive number. So since this is negative, that makes the velocity or the speed negative. This being negative, the significance of that is that the source is moving towards the observer. That's the significance of this answer coming out negative. However, if the observed wavelength, like this red light, is larger than the emitted wavelength, the green light, then this term is positive and you get a positive velocity as the answer. And that would be the case for this man right here. And the significance of getting a positive velocity in this equation is that the source is moving away from the observer. So you can get both positive and negative answers in using this equation. So then the question arises, if this is the light that you're observing, you're either observing this red light or this blue light, and you don't really know anything else about this object. This could be like a star that's emitting this light. How do you know what lambda naught is? How would you know what the wavelength it's emitted at if all that you're doing is observing the either compressed or stretched wavelength? How would you know what its original wavelength is? So that's the trick right there, and that's what we want to answer. The way that you do it is you look at the spectrum of the star in detail. And we've talked about this in previous videos, in particular in the video on the Bohr model of the atom, and we studied these things called the Kirchhoff's laws. But this is just why you either observe either an absorption line spectrum or an emission line spectrum, and we're mainly interested in this. So just a quick review of that. When you look at a star, you're looking at the light from the surface of the star, which is a blackbody spectrum, which means it's a continuous spectrum with all wavelengths. However, this light that's emitted by the surface of the star, this has to pass through the star's atmosphere. And that could be represented here, the cloud of cold or gas. So this would be the atmosphere of the star itself. And as this light passes through the star's atmosphere, the various atoms in that star's atmosphere will pick out very specific wavelengths of light, and that's why you see these missing wavelengths in the spectrum of that star. This is, they pick these wavelengths out due to the fact that the electrons in those atoms, so these would be the atoms in the atmosphere of the star, each of those atoms has a set of energy levels, and if the electron's in a particular energy level, it can get bumped up to a higher energy level, but it does that by absorbing a photon of that specific energy or that specific wavelength that's just right to account for the energy difference between those two levels. So that's the kind of the quick description of why you see these very specific wavelengths missing in the spectrum of the star. This is due to the various atoms in the atmosphere of that star just picking out all those photons that have just the right wavelength or just the right photon energy to correspond to a pair of energy levels. So here's the absorption line spectrum of the sun. So this is what the sun spectrum looks like if you really look at it in detail, and you see all these absorption lines, and you see that there are some very prominent ones and there are some much more subtle ones. It turns out that for the most part, all stars, or most stars, have a somewhat similar set of or pattern of absorption lines. Like in almost all stars, you'll see some hydrogen absorption line. In future chapters, we're going to see that some stars will have more prominent hydrogen than others. And in most stars, you'll see some calcium lines as well. Although, again, in some stars, they're more prominent than others. But for the most part, you'll always see those hydrogen and calcium and helium lines in pretty much all stars. And so you'll always be able to identify this characteristic pattern of absorption lines from the atoms that are typically found in the atmosphere of all stars, pretty much. So what you do is you look at the spectrum of a star and you compare it to and you identify all those absorption lines, and then what you do is you compare the wavelength at which you observe those absorption lines to the wavelengths that you know that they're emitted at. So like this would be like the spectrum of the sun right here. And what you could do is you look at another star, not the sun, and you see it looks just like the sun, except everything's shifted to the right. Everything's shifted to longer wavelength. That means that the star is moving away from us. And you look at this spectrum, you see that same pattern that you see in the sun, but they're all shifted to shorter wavelength. So you know that this star is moving towards us.